Good afternoon, everybody. Now let us start our today's class. Today we will study the complex integration. Complex integration class 3. That is my third class on this complex integration. So now I will tell you the statement of Cauchy's theorem. So what is the statement of Cauchy's theorem? This is, let f be a function which is analytic. Let f be a function which is analytic. Let f is a function which is analytic at all points inside and on a simple closed curve C. Inside and on a simple closed curve C. Simple closed curve. Simple closed curve C. Then integration over C f of z dz is equal to 0. So this is the Cauchy's theorem. This is the statement. If f, or you can say this is your f of z, let f of z be a function which is analytic at all points inside and on a simple closed curve C, then integration over C f of z dz is equal to 0. If f of z is analytic inside and on a simple closed curve C, then integration over C of f of z dz is 0. This is your Cauchy's theorem. Okay. So now comes to some other definitions. Let's simply connect the domain. What do we mean by simply connected domain? Sorry, simply connected domain. Simply connected region. Simply connected region. Okay. A region D is said to be simply connected. A region D is said to be simply connected region if every simple closed curve lying in D encloses only points of D. So what we understood from this statement, a region D is said to be a simply connected region. A region D is said to be a simply connected region if every simple closed curve lying in D encloses only the points of D. Suppose I will say this is a region enclosing all these points. Suppose I will give some different color here, some favorite colors. So I am coloring this region, and I will say this region as a simply connected region if this is my region D. This region is said to be a simply connected region if you take or if every simple closed curve. So if you take any simple closed curve, this is a closed curve. Okay. So if you take every simple closed curve lying in this region D encloses only the points of D. So this thing encloses only the points of D. This thing does not encloses any point which is outside of this region D. Okay. Since this thing encloses only the points of D, so this region D is said to be a simply connected region. Okay. Similarly, what is a multiply connected region? What is multiply connected region? A region D or a region D which is not simply connected, then that is a multiply connected. A region D which is not simply connected, which is not a simply connected region, not a simply connected region, it should to be a multiply connected region. Okay. So how the multiply connected region looks like? Suppose I will say this is a region. This is a region D, and this is if I will make these things, I'm saying this is a region which includes only these points, these things. Okay, these things only. Not including those points inside these three closed curves. This thing includes only these points. Okay. So if I will say a curve like this, this is a region D, this is a region D, which includes all these points which are in this yellow color. Okay, and there are three holes like this. There are three some closed curves whose inside regions are not in this region D, and this is said to be a multiple region because if I will take any closed curve, like suppose I will take this is a closed curve. So if I will say this is a closed curve and this thing does not include every point of D, because this thing includes this thing, it's okay because these things are inside D, but what are inside this small curve, these things are not lying in D, but this thing is lying in this closed curve. In this closed curve what I am taking, and this thing uh, containing these points, these insider points, but this thing does not contain in D. So if a closed curve lying in D does not encloses, or if it does not encloses only the points of D, that's why it is multiply connected. Okay, so this is a multiply connected. Similarly, if I will take this type of curve, this thing does not include these points, or this curve includes this point which are not lying in D. That's why this is not a simply connected, that is a multiply connected. Okay, this is the definition. Similarly, if I will take another curve like this, which is a annulus, so this is another region D, which includes only these points. Okay. So if I will take a region which includes only these points, so this is also a multiply connected. This is a multiply connected region, and this is also a multiply connected region. Okay. Because if you will take a curve like this, so if you will take a closed curve like this, so this thing includes these points, it's okay. This thing includes these points, but this closed curve includes this point which are not in D. So since this closed curve contains some points which are not in D, so that is multiply connected. That was my definition. Okay. This color does not lying in D, but this thing is contained in this closed curve. What is that closed curve? That thing lies. That thing includes this region, but this thing is not lying in D. That's why that is a multiply connected region. Okay. Then comes to next thing. Now comes to our Cauchy's integral formula. Okay. So I will write a statement and also I will prove it. Then what is Cauchy's integral formula? So what is the statement? Let f of z be a function. Let f of z be a function. Let f of z be a function which is analytic inside and on a simple closed curve C, which is analytic inside and on a simple closed curve C, which is analytic inside and on a simple closed curve C. Let Z not be any point. Let Z not be any point in the interior of C. In the interior of C, then f of Z naught is equal to 1 by 2 pi I integration over C f of Z divided by Z minus Z naught dz. Okay. Then you have to show this thing. F of Z naught is equal to 1 by 2 pi I whole into integration over C f of Z divided by Z minus Z naught dz. Okay, now I will prove it. So first we are saying that f of z is a function which is analytic inside and on a simple closed curve C. Okay, this is the simple closed curve. This is the simple closed curve C, and here we have to choose a circle whose center is z naught and radius is r naught. Okay, so this is the circle C naught whose center is z naught and radius is r naught. Okay, so I'll write this thing. Choose a circle. Choose a circle C naught whose center is z naught and radius is r naught, such that C naught lies such that this circle C naught lies inside C and lies in the interior of C. Mathematically, we can say this is the in the interior of C. Lies in the interior of C. Okay. C naught is a circle whose center is Z naught and radius is R naught. This thing is lies in the interior of C. Okay. Now Z naught is the only point. Now Z naught is the only point inside C such that f of Z divided by Z minus Z naught is not analytic. Is not analytic at that point. Okay. Z naught is the only point where this f of Z divided by Z minus Z naught is not analytic. Because if you will put in place of Z naught, then Z naught minus Z naught will be 0. This will be f of Z minus, so f of Z divided by 0, which is not defined. So not defined means it is not continuous. Similarly, it is not differentiable. Similarly, we can say this is not analytic. Okay, because at Z naught the function is not defined. This f of Z divided by Z minus Z naught. Okay, so we can say this Z naught is the only point. This is the only point inside C where f of Z divided by Z minus Z naught is not analytic. So you can write only this much. This is not analytic. Okay. Hence what we can say? Hence we can say that f of Z divided by Z minus Z naught is analytic. This is analytic in a region D consisting of analytic in a region D consisting of all points inside this curve C except the points inside C naught. But then at the point Z naught, that function is not analytic and this Z naught is containing in C naught. So if I am excluding this C naught, then after that it is analytic on C except this C naught. So if I will remove this C naught or excluding this C naught, it is analytic outside of this C naught. And I am saying that is my region D where it is analytic outside C naught. Okay. And I am saying that is my region D. Okay. So f of Z divided by Z minus Z naught is analytic in a region D, and this region D consisting of all points inside C except the points interior to C or except the points inside C naught. Hence what we can write? Hence I can write the integration of C f of Z divided by Z minus Z naught dz. This thing will be only integration of C naught f of Z divided by Z minus Z naught dz. Okay, because it is saying that this function, this f of Z divided by Z minus Z naught is analytic in the region D, and it is analytic in the region D means this is the region D. I already told you the region D. What are the points which are inside C but outside of this C naught? Okay, so this is my region D, and I am saying this analytic there. So I already told you the Cauchy's theorem, where it is where the function is analytic at that region, its integration is 0. So since its integration is 0 in the region D, so integration over C means it will be only integration over this C naught. Okay, because outside of this C naught and which are inside C and outside this C naught, that is the region D, and there the function is analytic, so there the integration will be 0. So integration over C means this will be only the integration over C naught. Okay, by applying, or you can say, since integration over D f of z divided by z minus z naught dz is 0, where d means this is C minus C naught. Okay, by applying Cauchy's theorem. By applying Cauchy's theorem, because Cauchy's theorem says where it is analytic, a function, if it is analytic in a region D or in a region C, then its integration over that region or over that curve C is 0. I already told you this Cauchy's theorem. So now integration over C means this is integration over C naught. Then what I will write? Then integration over C naught. In place of f of z, I can add this is f of z minus f of z naught plus f of z naught whole divided by z minus z naught dz. Just I am subtracting an f of z naught and adding f of z naught. So this will be same. Now comes to next page. So the left hand side is integration over C f of z divided by z minus z naught dz. On the right hand side, I can add this is integration over C naught. This is I am rearranging f of z minus f of z naught divided by z minus z naught dz plus integration over C naught. This is f of z naught divided by z minus z naught dz. Okay. Then I can add this one as this is integration over C naught. This is f of z minus f of z naught divided by z minus z naught dz plus, here you can take this f of z naught outside of this integration, then integration over C naught. This is 1 divided by z minus z naught dz, and we know its value because I already told you in my last class. Integration over C 1 divided by z minus a into dz. This is a 2 pi I, where C means C is a circle. This is z minus a equal to r. That means this is a circle whose center is a and radius is r. And integration over C z minus a divided by 1 by z minus a dz. This is a 2 pi I. So here I will put something. I will write here. So this will be same. So this is your f of z minus f of z naught divided by z minus z naught dz plus this is f of z naught and this value is your 2 pi I. So I will write this is 2 pi I. Then this is your integration over C f of z divided by z minus z naught dz. And if you say what you want to prove, this thing should be equal to this one. This is our motto, or this is our aim. We have to prove this one. So now what we can claim? Now we can claim that this integration must be 0, because we have to prove the first one is equal to this one is equal to this one. So this thing must be 0. So now our next claim is to show that. Now our claim is to show that integration over C naught f of z minus f of z naught divided by z minus z naught dz is equal to 0. Okay. So this is our claim. Claim is that is our next time we have to show this thing. Okay. Uh, since f of z since f of z is analytic, inside and on C, then we can say that f of z is analytic at z0 because z0 is lying inside C. So since f of z is analytic at C, so f of z is differentiable at C. Also f of z is continuous at C. So f of z is continuous at C. Continuous at this z0. At z0, since it is analytic, it is differentiable and also it is continuous. So f of z is continuous at z0. So that means we can say, given epsilon greater than 0, there exists delta greater than 0 such that z minus z0 less than delta implies f of z minus f of z0 modulus is less than epsilon. This thing we already know from this, the epsilon delta definition of continuous of a function at a point z0. Okay, so if we choose our r0 is less than delta, r0 means the radius of this circle c0, because we took the circle c0 as this is z minus z0 equal to r0, because c0 is a circle whose center is z0 and radius is r0. So if I'll make that circle is very small, that means its radius is very small, r0, that is the r0. So if I'll choose my r0 is less than delta, then your z minus z0, this one, z minus z0 will be less than r0, implies f of z minus f of z0 modulus will be less than epsilon. Now the next page. So now then what we can write, hence we can write the integration of c0, integration over c0 of f of z f of z minus f of z0 divided by z minus z0 of dz modulus is less than, you can simply write this is strictly less than, strictly less than epsilon by r0 whole into 2 pi r0. How you can write this thing, because we already read one theorem, integration over c of f of z dz, this thing is less than m into L, where m is the maximum value of f of z such that z belongs to C and L is the length of curve C. So if m is the maximum value m, this m is the maximum value of f of z where z belongs to this curve C and L is the length of curve C, then you can say integration over C f of z dz is less than ml. And here you know f of z minus z0 has maximum value epsilon and this z minus z0 has maximum value r0. So this is the function, this has maximum value, this epsilon divided by z minus z0, and what is L? L is the length of c0. C0 is a circle whose center is z0 and radius is r0. C0 is a circle, so what will be its length? Length will be its the perimeter. This is 2 pi r and here r is equal to r0. So the length is, so in place of L I will write 2 pi r0 and in place of m I am writing this is epsilon by r0, because you know This value is maximum value of f of z minus f of z naught is epsilon, and the maximum value of z minus z naught is r naught. So this is epsilon by r naught, 2 pi r naught, which is equal to r naught can cancel out, then this will be 2 pi epsilon. Okay, so that's what we can write. You can say here what will be my equation 1. Let this is my equation 1. Okay, which says that integration over c of f of z divided by z minus z naught dz is equal to this one plus this one. Now I evaluated, this one is equal to 2 pi, this thing is less than 2 pi epsilon. Okay, so if I will make this thing as 0, then this one will be my this one. So now I'll put this thing as 0 after one step. So what we can say, integration of this one is less than 2 pi epsilon. But since epsilon is arbitrary, can write this thing. Since epsilon is arbitrary, since epsilon is arbitrary, this implies integration over c naught of f of z minus f of z naught divided by z minus z naught dz modulus is less or this one is equal to 0. Since epsilon is very small and arbitrary, so integration over c naught, this thing is equal to 0. Okay, so now since this thing is equal to 0, from 1 already I told you what is my equation 1, which is in my last page. So from equation 1 we get integration over c f of z divided by z minus z naught dz is equal to 2 pi I f of z naught, or you can say your f of z naught is equal to 1 by 2 pi I integration over c f of z divided by z minus z naught dz. Okay, so this is your Cauchy's integral formula. Now using this formula I will do a problem. Consider integration over c, this is dz divided by z minus 3, integration over c dz divided by z minus 3 is equal to, or we have to find this one, where c is the circle, z minus 2 is equal to 5, z minus 2 modulus is equal to 5. Okay, see the curve c is given to you, and you have to evaluate what is the integration of c dz divided by z minus 3. So if we will see what is the curve or what is the circle, what is the equation is given to you. Suppose this is origin 0, this is 1, 2, 3, 4, 5, 6, 7, 8, and this is minus 1, minus 2, minus 3, minus 4, like this. This is 1, 2, 3, 4, 5, and then here minus 1, minus 2, minus 3, minus 4, minus 5. So what will be my z minus 2 modulus equal to 5 means its center is 2, radius is 5. So this is a circle whose center is 2, so this will be here, and radius is 5. So this is 1, 2, 3, 4, 5. So here 5 is this one, then 1, 2, 3, 4, 5. Here 5 will be this one, then here this line, and here also this line. So if you will draw a circle, this will be like this. Okay, whose center is 2 and radius is, this is 5 unit. Okay, so if we'll see the point, what is z minus z naught? Here z naught is 3 and 3 is this one, which is lying inside this circle C or inside this curve C. So here you can write here f of z is 1, because f of z divided by z minus z naught, and z naught f of z is 1, then 1 is a constant function. Okay, so here f of z is equal to 1, you can say, which is analytic, inside and on the curve C, and z naught is your 3, which lies inside C, which lies inside this curve C. So by Cauchy's integral formula, what we can write, integration over C f of z divided by z minus z naught dz is your 1 by, sorry, this is 2 pi I f of z naught. This will be your 2 pi I f of z naught. So if I will put this thing, f of z is your 1 and z minus z naught is your 3 dz, this will be 2 pi I f of z naught is your 3, and since your f of z is 1, so f of 3 will be 1 is constant, so what is your f of 3? That will be also 1. So this will 2 pi I into 1, which will be your 1, 2 pi I, sorry. This is your 2 pi I. Okay, so this is your answer. Now comes to a statement only. What is maximum modulus theorem? Maximum modulus theorem. Maximum modulus theorem. Okay. So what is maximum modulus theorem? Let f of z be continuous. Let f of z be continuous in a closed and bounded region D, in a closed and bounded region D. Okay, and analytic and non-constant, in the interior of D. In the interior of D, then f of z modulus attains its maximum value on the boundary of D. On the boundary of D, never in the interior of D. Never in the interior of D. So if f of z is continuous in a closed and bounded region, the region D is closed and bounded, and f of z is said to be continuous on that region, and f of z is analytic and also non-constant. F of z is not constant, okay, and also it is analytic in the interior of D. Then f of z modulus attains its maximum value on the boundary of D. So what is the region D? So on its boundary, the f of z modulus will attain its maximum value. Okay, never in the interior of D. So in the interior of D, mod f of z is not maximum. Its value is maximum only on the boundary of D. Okay, so now comes to so let it be problem 2. Evaluate divided by z square plus 4. Okay, where C is positively oriented circle, z minus I mod is equal to 2. Okay, so first I will say what will be my C. The circle C, its center is, this is a circle whose center is I and radius is 2. So if I will draw what is my C, this is the origin O, this is 1, 2, 3, 4, this is minus 1, minus 2, minus 3, and this is 1, 2, 3, then minus 1, minus 2, minus 3. Okay, so center is at I, so I means here in imaginary axis 1 and its radius is 2. So this will be 2 unit, here it will be 2 unit, then here it will be 2 unit, here it will be 2 unit. Now draw the circle. Okay, this is the circle whose center is I. Okay, so now comes to what is my f of z. Here you can say your f of z is e to the power z, and here it is z square plus 4. So after leaving this f of z, what is there? This is z square plus 4. So I can write z square plus 4 as z plus 2y, z minus 2y. And you know the partial by parts. So by using by parts, you can write this thing as this is 1 by z minus I minus 1 by z plus I. So if you will write this thing, then there will be a 4I in the numerator, and after dividing that one, then you will get this is your this one. You know by parts you will use it by using by parts. Okay. So by using by parts, you know this is where this one. So sorry, this is z minus 2y, z plus 2, z minus 2y, this is z plus 2y. So what I can say here 2y, 2y where it will be, this is your point 2y, this one. Okay, so this one lies inside the circle, this 2y. Here you can say here 2I lies inside the circle C, but minus 2y will be somewhere here. Okay, and this is outside of the circle. Minus 2y means in imaginary axis or in the negative imaginary axis you have to say the 2 unit. Okay, this will be this one. Okay, here 2y lies inside the circle C, but minus 2y lies outside the circle, C. Okay, so if I will evaluate the integration over this one, which will be in outside this circle, for that the integration will be 0, and what will be inside, if that z naught is lying inside the circle, then you know how to apply that Cauchy's integral formula. Okay, so if I will go to that thing, what will be my integration of this one? I can write the integration of okay, I will write this one, integration of e to the power z divided by z square plus 4 dz can be written as, this is integration over c, and in place of z square plus 4 I will write this thing. So this is e to the power z divided by 4i, then in place of z square plus 4 I have already written this one, 1 by 4i, then 1 by z minus 2i minus 1 by z plus 2i dz. Then this is integration over c e to the power z divided by 4i, 1 by z minus 2i dz minus e to the power z divided by 4i. You can take this 4i outside of this integration. Okay, so I will write 1 by 4i here. Then this is e to the power z whole into 1 by z plus, here z plus 2i means z plus 2i, that means z minus 2i dz. Okay, so this is 1 by 4i whole into, this is e to the power z, this is, that is your f of z. You can say this is your f of z, which is analytic, because e to the power exponential function is analytic everywhere. This is analytic inside and on C. Okay, so since it is inside, analytic inside and on C, and here this is the point 2y, this is the point z minus z naught, that means z naught is your 2y and 2y is lies inside the circle. So by our Cauchy's integral formula, this thing you will be right, this is 2 pi I into f of z naught. So f of z naught means f of z is e to the power z, so 2 pi I e to the power 2y. Okay, minus, and here this minus 2y I already wrote here, minus 2y lies outside of this circle. So that means what is your f of z, or this thing divided by this one, this is analytic inside C, because this uh, if I will consider this function e to the power z divided by z minus 2y, so this thing is analytic in the whole curve C. Okay, this thing is not analytic at minus 2y, but minus 2y is lying outside this curve C. Okay, this minus 2y is lying outside of this circle C. So I can say this is analytic inside C. So since a function is analytic inside C, so by Cauchy's integral, its integration value is 0. So this will be 0. So only what will left, 1 by 4 pi I, sorry, 1 by 4i into this one, which will be pi by 2 e to the power 2i, pi by 2 e to the power 2i. So this is your answer. So you have to find after that means what is my n. So if in the denominator there is a function like this, by using by parts or by using this partial fraction, you have to linearize this thing. After linearization, whatever you will get your z minus z naught, then you will see where the z naught is lying. If z naught is inside the circle, then you will use the Cauchy's integral formula. Cauchy's integral formula. Okay, if z naught is lying inside circle C, and if z naught is lying outside the circle C, you have to use Cauchy's integral, sorry, Cauchy's theorem. Cauchy's theorem is saying integration over C f of z dz is equal to 0. if f of z is analytic inside and on C. And Cauchy's integral formula what says? Integration over C f of z divided by z minus z naught dz is equal to 2 pi I into f of z naught. Okay. So that means whatever I am writing here, this thing is not analytic at z naught, and z naught is lying inside C. So if z naught is lying inside C, so by using Cauchy's integral formula, its value is 2 pi I f of z naught. Okay. So this is the thing. Similarly, I'll do my last problem. So what is my problem? Find the integration over C of this is cos z divided by z whole into z square plus 8 dz. And what is my curve C? C is the curve C. This is a square. This is a square whose x is equal to plus minus 2 and y is equal to also plus minus 2. So what will be my C, curve C, or what is my square? This is 0, this is 1, 2, like this, 3, 4, like this. This is 1, 2, 3, minus 1, minus 2, minus 3, minus 1, minus 2, minus 3. So what will be x equal to plus 2, x equal to minus 2 means these are the things, and y equal to plus 2 minus 2, then y equal to this one, this one. So this is my curve C. Okay. So how we will solve this thing? So if you will see what is the denominator, this is z whole into z square plus 8. So if you will linearize this thing, and if you will see the points here, if I will make this thing into 0, so z will be equal to 0, and z square plus 8, that is your z plus 2 root 2i and z minus 2 root 2i. Okay, 2 root 2. Okay, so this is this one. So if I will see the z naught here, so z naught will be minus 2 root 2i. Similarly, what will be here z naught? Z naught will be here 2 root 2i, and all these things are lying outside of this curve C, because in this curve C up to 2 you will get that 2 root 2 means here it is 2, in imaginary axis here it is 2, so 2 root 2 means this is more than 2, so this will be outside C. Similarly here minus 2 root 2i, this will be also outside C somewhere here. So z square, if you will see this z square plus 8, or we can say here let f of z is equal to, this is cos z divided by z square plus 8, which is analytic. Why I tried these points? Because this for this thing, if I will take this is my f of z, I can say this is analytic inside and on C. What is my curve C? This square. So inside this square, this thing is analytic. So I can take this is my f of z. Okay. So if this will be my f of z, then what will be my problem? This is my f of z divided by z dz, because only z will left. Cos z divided by z square plus 8 is my f of z. So what will be this one? And this is z means this is C, f of z divided by this is z minus 0. So z minus 0 means you can say this is by using, and here 0. this 0 is lying inside this curve C, since so you can write